Hello, Math 2413 student. Here's lesson 14, the definite integral 2. This is a continuation of lesson 12, the definite integral 1, which covered up to section 3 of this notebook. Lesson 14 begins from section 4, Riemann sum and Riemann integral. And this entire theory is based upon a contribution by this gentleman, Bernhard Riemann. And of course, there were other people too, many others, but his contribution was the greatest, so we usually refer this theory as Riemann's integral and Riemann integration. Okay, let's begin. The theory of Riemann integral begins with the concept of partition. Given closed and bounded interval a to b, a partition in that interval is a finite sequence x0, x1, x3, and so on, all the way over to xn, which is a strictly increasing sequence that begins from a and ends at b. So x0 is equal to a, and xn is b. And then we have x1 through xn minus 1 in the interior, in the increasing order. Consequently, we get n subintervals. Down here, we have a visualization. First subinterval, and then the next subinterval, the third subinterval, which is by far the longest, and the fourth subinterval here. In this particular case, n is 4. Of course, you can consider n value as 100. In that case, it's going to be a lot more difficult to visualize that. Now let's consider the length of each subinterval. Delta x1 is the length of the first subinterval, x1 minus x0, and delta x2 is the next subinterval, x2 minus x1. Delta x3 minus x2 is the longest in this particular case. And then finally delta x4. And of course, if n value is bigger, then you can consider hundreds of subintervals like that. We use Greek letter delta to represent the difference. And yes, indeed, the difference is xi minus xi minus 1. And that's the interval length, the subinterval length. And among those, the biggest is referred to as delta x without the index. That's the maximum. In this particular case, delta x is delta x3. Now what we are going to do later is to take this delta x going down to 0. So maximum is going down to 0. Consequently, everything will go down to 0. Make sense? Okay, that's what the partition is all about. Next, let's define Riemann sum. Given partition, given subinterval, we can consider a Riemann sum like this, yi star times delta xi. So delta xi is the subinterval length, yi star is going to be the height if you draw a graph. Let me show you. Here's an example. So we have 4 subintervals, the same subinterval we saw before, and then we selected y values at random between the minimum and maximum. In this case, y1 is very close to the minimum, maximum, close to the maximum, and then y2 is somewhere in between, pretty close to the midpoint, a bit lower than the average. And in this case, y3 is close to the maximum, but not this close. And y4 looks like it's about the average. This program is randomized, so you can run it again. And each time you run, you get different y values. In this case, y4 value is very, very close to the minimum. You can see that. And if it reaches the minimum and becomes 0, then looks like you have no rectangle here. But as a matter of fact, you do have a degenerate rectangle of height 0. Now, what does this Riemann sum represent? Y times delta x, that's the area of each rectangle. Y value is the height, delta x is the width. And then summing them all up, what you get, we have the sum of the areas of all these rectangles here. In this particular case, there are 4 rectangles, so 4 areas are added up. But if the partition size is much bigger, then you may have hundreds of those rectangles. That's the Riemann sum. one more thing. For continuous functions, this yi can be rewritten as f of xi star. Let me show you the visualization. Oh, no, this one. So arbitrary y1 between the minimum and maximum, that corresponds to a certain function value, f of x1 star. And then y3 star, yes, that's f of y3 star, x3 star, and then so on. But look at the middle rectangle. This top line does not cross the graph, so this y-coordinate value does not correspond to the function value of anything. So in this particular case, for this red rectangle, f of x2 star is invalid. That's because we have a discontinuity. For continuous intervals, always we have appropriate function value. Always you have those. Well, in this particular case, even the red rectangle has appropriate function value. F of x2 star is going to be very close to the function value of x1 right here, it appears. But not always. That's because of the discontinuity. In this case, yes, we have crossing, so we have a function value. But in general, no. But for green rectangles, always we have function value. So in short, the Riemann sum, which is in general written like this, where yi star is any y-coordinate value between the minimum and the maximum, can be reduced to function value f of xi star if the function is continuous. No, not this one. This one. You see, for continuous intervals, all okay. For discontinuity, no. So if there's no discontinuity, then you'll have f of xi star everywhere. Okay, all right, that was one reduction. Let's go one step further. In a special case, all the delta xi's are the same. In this case, the lengths are all different. Arbitrary. So given n value, in this case 4, and then selection is arbitrary, you can consider various subdivision as long as there are 4 of them. And an n value is say 45, then you're going to get 45 rectangles and you're going to get various subdivisions arbitrarily. That's what the general Riemann sums are all about. But in a special case, we can consider evenly spaced Riemann sum where all those subinterval lengths are identical. Let's see, do we have a visualization for that? I'll show you a bit later. It doesn't come with that, but the final expression here appears in our textbook. So this one here is not general enough as a matter of fact. It appears in the textbook, but as a matter of fact, this is very, very thinned down version. Go a little bit further, you can consider unevenly spaced Riemann sums for continuous functions, and go even further, you will have the general form. Unevenly spaced, and even the y values are anything between the minimum and maximum, and the function does not have to be continuous. For continuous functions, visualization is relatively reasonable, and I'll show you some of those. Let's see, I think I have those programmed here. Okay, all right. Let's begin with a continuous function. I already showed you a discontinuity case, so let's stick to easier case, continuous case. And the first program visualizes n value 20, so 20 rectangles where the subdivision is selected arbitrarily. As you can see, this approximation is pretty bad. What we want to do is the Riemann sum, that is sum of the areas of the rectangle, and does it correspond to the signed area? And it looks pretty bad. The signed area is supposed to be 3.19 something. Yeah, I mean, remember the signed area concept? We talked about it in section 1. And that makes sense when we have a graph of a continuous function. If it is not continuous and then the graph is too complicated, entire idea of signed area collapses. So you have to consider the Riemann sum. But in this particular case, the graph is continuous, so it's okay. So signed area is 3.19 something. And the approximation by those rectangles, oh, that's pretty bad, 4.11 something. As you can see, we have really fat rectangles here and there. Let's run it again. Do we get something better or worse? Maybe a little bit better. Still better? No, not really. We still have some really fat rectangles. Oh, this one is really bad, really fat rectangles. These kind of terrible things can happen if you have arbitrary Riemann sum. Is this good? In terms of computation, this is terrible. In terms of theory, however, this is good, very good, because we have to establish this Riemann sum in general. And how do we establish it in general for arbitrary continuous function, or even more, piecewise continuous function, or even more, Riemann integrable function, which we are going to consider in the next section? Well, we have to consider the worst possible situation and make an argument that it still works. So the more terrible approximation we get, the better in terms of theory. The worse in terms of computation, but the better in terms of theory. That's what you're looking at for arbitrary Riemann sum. We're going to come back and discuss the Riemann integral in the next video. For now, let's stick to Riemann sums. So we showed you some terrible case, arbitrary case. Now let's consider evenly spaced Riemann sums. In this case, no matter how many times I run, the intervals do not change. Width of all these rectangles stay the same. 20 rectangles evenly spaced. The height will change arbitrarily between the minimum and the maximum. And if you look at this Riemann sum value, yeah, that's pretty close to what it's supposed to be. So in terms of computation, this is far more effective. In terms of theory, that's too specific. Next example, midpoint approximation, and this is great in terms of computation. In terms of theory, it's useless because there's no randomness there. We simply take the function value of the midpoint of the interval as the y-coordinate, so there's no randomness. Still, it's an effective way to approximate. Another approximation, this time midpoint of the y-coordinate value. The average value, or midpoint value rather, midpoint of the maximum and the minimum, maximum and the minimum in the middle. See that? There's no randomness, so even if I run it again, I get it's the same picture. Another good way to approximate, and this is not rectangle, but we have a trapezoid approximation, kind of like interpolation, and we have, triangular or trapezoid approximation, and areas of those trapezoids turns out to be identical to the areas of these rectangles here. You see? This is the midpoint of the maximum and minimum. Not maximum and minimum, excuse me, yi and yi minus 1. And then this one, area of the trapezoid, again the same. And then we can consider left-hand side and right-hand side approximation. Please look at these two, and then height of the rectangles are given by the function value of the left-hand side versus the right-hand side of each interval. They're all Riemann sums. And the worst of the worst is, of course, the arbitrary case. And if this works, then everything will certainly work, because this is the worst possible situation. How does it work? Well, that's something we're going to answer in the next video. Stay tuned.